Check, check. All right. Hi, everyone. My name is Matthew Shoup. I'm the Senior Director of Insights and Partnerships at LeoLabs, and I'm going to take a few minutes and tell you about LeoLabs and what we're doing as a company, how we're tracking tens of thousands of objects in space, and how AWS plays a crucial role in that. All right, so I want to start off by presenting these two pictures that you see here and viewing that as sort of a tale of two different space eras, yesterday and today. The image on the left probably needs no introduction, but I'm going to give it one anyway. That's the Hubble Space Telescope launched by NASA more than 30 years ago, still operational today. The image on the right shows the payload stack of satellites atop the SpaceX Transporter-1 rideshare mission that launched in 2021. And in that one image is 143 individual satellites that were all deployed at the same time. So this kind of gives you a flavor of how things were done many years ago and how things are starting to be done now. So what does that mean? It means the space environment itself is actually changing, and it's not even a linear change. It's actually an exponential one in terms of the growth that we're undergoing right now. So the older way of doing things is really where governments launched low numbers of very big, very expensive satellites, usually one at a time, right? Now we're in an era that's dominated by commercial innovation and opportunity, with companies like Planet, who are launching hundreds of CubeSats to image the Earth every day, or SpaceX launching thousands of satellites to provide broadband internet. And we have very high numbers of smaller, lower cost, more agile satellites, usually with shorter lifetimes. And when you make this switch, that does mean that the space environment does get more crowded. There's no way around that, right? So that's not necessarily a bad thing, but it does mean we need to pay extra close attention as we launch more and more stuff into space, make sure we do it responsibly so that accidents don't happen. Because inherently there is more uncertainty and more risk when the orbital regimes are more populated. So that's our mission at LeoLabs, is to take on that challenge and track and characterize tens of thousands of objects in low Earth orbit to keep space safe. If you're not familiar with the acronym LEO, it stands for Low Earth Orbit, and it's the orbital regime, or the orbital neighborhood, if you will, that's closest to the Earth where satellites orbit. So there's LEO, there's geosynchronous Earth orbit, there's interplanetary orbits. LEO is by far the most crowded orbit regime now. It's where the International Space Station is, it's where thousands of operational satellites are at, it's where over 10,000 pieces of debris are located, bigger than the size of your fist. How do you track all that stuff every day, right? We do that at LeoLabs through a vertically integrated technology stack of hardware and software for space operations. The hardware side of that is a global network of what's called phased array radars. We design and build and operate these and deploy them at different geographic sites around the world. So these are our own radars, our own technology. 3 of them are shown here. The image on the top is our newest one in the Azores Islands off the coast of Portugal. The one in the middle is our Costa Rica radar, and the one at the bottom is our New Zealand radar. And we have several more that exist and that we're building still right now. So we operate these radars. They're on the ground looking straight up into space, and they have kind of this fan-shaped field of view that goes up a couple thousand kilometers, and objects just go through them, and we track them, and we measure their orbits, and we run event detection services to characterize what's actually happening. We then make services for our customers. We utilize the traditional SaaS model, and we make curated services for satellite operations and a number of other things. So the software side of that, so we talked about the hardware, that's the radars. The software side of it is a cloud-based computing platform built on AWS. It's really the backbone of our whole computational infrastructure. It takes the measurement data we get from those radars as they're tracking thousands of objects per hour, and we send that data from the radars to AWS, and a whole bunch of advanced astrodynamics algorithms happen from that point in the cloud. So we'll take those measurements, we'll fit pristine, very accurate orbits to each of those objects, and then we'll run some event detection and machine learning type algorithms to create our services. We've been operational as a company since 2016, scaling up rapidly. We have about 120 employees, and we are headquartered in Menlo Park, California, with offices around the world. We generate an enormous volume of data, more than 500 million data products each month. A lot of those we use internally to make our own services better, and many of those our customers use directly through either our user interfaces or our APIs operationally. And we support about 2/3 of all the operational satellites in LEO today, because we have paying customers such as SpaceX, OneWeb, Planet, Maxar, and many others, which cumulatively make up most of the operational satellites. The customer markets that we serve, we generally describe the markets that we want to provide our services to in 4 different verticals. The first one we just spoke about, commercial satellite operations. So we track the space debris in low Earth orbit directly, and we can predict what's going to happen in the next few days. So if I'm a satellite operator, we can send alerts and say, hey, you're going to have a pretty close call with this one piece of debris in like 12 hours from now. And then they can take that. There's always some risks and analytics associated with it. And then they can make the decision if they want to fire the thrusters on their satellite and actually maneuver out of the way. We serve governments around the world, both the US government and governments of allied nations, both from a defense and a civil perspective with capabilities such as space domain awareness and regulatory compliance and space traffic management. And then the fourth vertical is kind of where companies or entities who are not directly operating satellites in space, but they're stakeholders nonetheless. So things like space insurance companies or space investment firms who they have some skin in the game in terms of like what's happening up there, and they want to make sure that the coverages they're providing to their clients are right in terms of assessing orbital risk of flying satellites in certain neighborhoods. With that, we'll watch a quick overview video now. We need audio.
The problem that LeoLabs is solving is tracking and knowing where everything is that's orbiting the Earth so that we can allow greater use of space, greater profits to be had in space, and greater security in space.
We have built and we operate a modern space infrastructure stack that consists of phased array radars on the ground, looking up into space, tracking thousands of objects in low Earth orbit. Essentially, you can think of it as like a living map of space. The trajectories and coordinates of all the objects up there, the satellites, the debris, updating continuously every second throughout the day.
Getting hit by something even this big is still really bad. Those objects can be moving relative to you up to 14, 15 kilometers per second. So even getting hit by something as small as 2 centimeters across will totally ruin your day, and perhaps the day of your business or the year of your business.
When you see the ultimate outcome, which is, we're actually helping keep space safe, that is a reward that it's just hard to describe. It feels good.
All right, thank you. I look forward to this fireside chat.
Araz, would you like to come up and introduce yourself?
Thank you, Amazon, for having us. My name is Araz Faizi. I'm the co-founder and CTO at Kayhan Space. Before I get started, quick question for the audience. By show of hand, who comes with space background in the audience? Okay, great. That's what we want to see. All right, so on the left, kind of same theme as what Matt showed earlier. On the left side, that's Apollo 13. There were yokes, physical keys, physical bottle handles that astronauts used to fire thrusters, to make burns, to change trajectories. In this particular mission case, with what happened, go around the moon and come back safely to Earth. On the right-hand side, fast forward 50 years. This is just from a few months ago. Falcon 9 launches autonomously, deploys a payload. Then you have Dragon that flies autonomously, performs rendezvous and proximity operation, autonomously docks with ISS, and they can offload, whether it's the supply that it's bringing or the astronauts, and it autonomously flies back and brings astronauts safely to Earth. 50 years apart, we went from flying our spacecraft completely manually to flying everything autonomously. Well, one obvious reason is that now there's technology that's allowing us to do that. But there's another reason. As Matt explained, and as we will talk more, space is getting congested and more contested. And humans are simply too slow to be in the loop of performing space operations. And that's why we started Kayhan Space. We're a software company. We're developing tools and autonomy to make spaceflight safer for space operators. We do that because the space industry has changed quite dramatically. In old space, you had to be one of those multi-billion-dollar corporations or a space or a government agency to be able to plan, launch, and operate a space mission. Today, you can be a small company, funded in a seed round, and get to space. And one of the reasons is tools that companies like us are building to allow it. Imagine you have to pave a road, right? And you have to build all the equipment you need to pave the road. How slow would that be? Or imagine today where you can buy the equipment, buy the services, and focus on what matters the most, your mission. And that's what we're doing. So small company, 3 years old, 20 people out of Boulder, Colorado. We have a group of, we have aerospace engineers, astronomicists, software engineers, and innovators building tools. So what problem are we trying to solve? There are estimated 1 million pieces of debris larger than 1 centimeter in diameter in Earth orbit. We are tracking somewhere between 20 to 50,000 of them reliably. And even with those 20 to 50,000 that we're tracking, a small object, size of a penny, traveling at 17,000 miles an hour can destroy a satellite. So we need to make sure that, first of all, our assets in orbit are safe from colliding with debris and also from colliding from other assets in orbit. The first product that we've developed is called Pathfinder. It's a cloud-based software solution that allows satellite operators to avoid collisions autonomously. What we do is that as a customer, when you're onboarded, let's say you have a constellation of 100 satellites, you can come to Pathfinder and you can see all the high-risk events that you have in front of you. You have 5 very high probability events that we recommend that you need to perform a maneuver to get out of the way. The rest, we're gonna track them. We're gonna keep an eye on them to make sure that you're safe. But when there is a need for a maneuver, and that's where our main service comes to play, we provide our satellite operators with maneuver plans that they can simply execute on their satellite. So, if you want to perform a burn and get out of the way of a collision, you have, unlimited opportunities, but there are certain ones that work because of the constraints that you have, because of your capabilities. By doing that, by automating that process, we're reducing the response time to potential collision events by about 90%. The second product that we have on the market, this one is we developed it internally. So when we wanted to develop Pathfinder, we realized that the open source software that exists out there that are developed by academia, by NASA or other agencies, they're just not built for cloud. And that's what we need today, right? So you can't really take a software that's written in Fortran or a model that's built for MATLAB. So we developed an in-house tool called Eagle that is a very high performance, high fidelity propagation engine. So what that means is that it can simulate the motion of objects in space from very low Earth orbit to cislunar very, very rapidly. And that's kind of core to whatever that you want to do in space. So it is multi-platform architecture. So today it's cloud-based. It's deployed in Azure, in AWS. It is available on the marketplace. You can use it through APIs. You can use it through software development kit, and the list goes on. The other great thing about that is that even though it's a microservice today and it's accessible through APIs and all that, you can deploy it on board if you want to. And that's one of the beauties of this product. And the last but not least, Gamut. Any mission that you want to launch, a Falcon 9 mission, it's an Ariane, you name it, before you launch, you have to make sure that the main aircraft, the secondary, everything, any components that come out of it, the payload is safe. And generally, your launch window opens, let's say it opens at 12 o'clock at noon and it closes at 2 p.m. So you have 2 hours to launch, and you have the option to launch at any second. That is not one problem, that's 7,200 problems. So we've developed a GPU-based model that is deployed in AWS Cloud that runs order of magnitude faster. So as a launch provider, you can quickly run your mission through that platform, through Gamut, to make sure that your flight is safe before you go for licensing and before you go to launch. And with that, I'm going to stop so we can get back to the conversation. I'm looking forward to questions from the audience. Please. There goes.
Thank you so much, Araz. We're actually going to put up a live demonstration right now of tracking debris in space while we get ready to do a fireside chat on how is it that we came to this point, where do we need to go, and what are our thoughts on tracking the complexity of space. So to start off, and I'll give you, Matthew, a moment to sit down, but Araz, to start with you, is space too crowded?
So, the analogy I like to use is that it's like a road. You can drive anywhere you want, but there are certain roads or highways that get crowded. And it's the same thing with space. So you have certain orbital regimes, certain orbits that are more popular because of their nature. For example, Sun-Sync orbit is really popular for Earth observation. It's getting more crowded. So yes, space is big, right? There's some study that showed that the carrying capacity of Earth orbit, 95% of it is taken up by space junk. But space is big. So that assumes that the capabilities that we have today to track those and capabilities that these satellites have to avoid collisions with each other or fly autonomously. So it is crowded. I guess the short answer is it is crowded, but by advancing the technologies that we're using, we will be able to expand that capacity and take advantage of more of these orbits.
Same to you, Matthew.
Yeah, this is an interesting question. It's sort of a hot topic in the space industry right now. You know, what is too crowded? Like, what does that mean? I think it's a question that requires context, right? So, too crowded to do what? What's the second part of that? Clearly, many more satellites could physically fit in space in different orbits, but that's not what we're talking about. There are, in the analogy of orbital highways to road highways, think of highways in space as like almost shells around these concentric shells around the Earth. Certain altitude bands are very crowded, and then some others are not, right? And then you might have a constellation that's operating up here, and another one that's going to operate up here, but they have to like orbit raise up through, one goes up through the other one. All kinds of coordination needs to happen. So I think in terms of, is it too crowded or is it getting too crowded? My answer right now is no, but it's a no with a little asterisk by it. Like, no, but I'm in agreement with Araz, if there's best practices that have been pretty well established amongst our industry that if they are followed and adhered to, and a lot of that is like operator communication with one another, doing active collision avoidance. When your satellites are done with their mission lifetime, deorbit them back down as soon as you can. Don't just leave stuff up there for decades. And actually remove debris itself to prevent future collisions. It's definitely a system that requires sort of global partnership and interacting because space is a shared resource. Space is not the same as like airspace, where there's the US and then there's Russia or India or whatever. Like when you put something into orbit, it starts orbiting and the Earth spins underneath it. So that means every satellite that goes up goes over every point of the Earth, essentially, depending on its inclination. So we can talk a little bit more about some of those best practices if we want, but I do think if we follow the best practices that have been talked about quite a bit, that there is a good bit more of space that we can occupy, including different orbital regimes.
I actually want to add another analogy here. So now imagine take like a 2-lane road, sized road. There are no markings, no signs. There are bicycles on it, people just walking across it, and cars driving in any direction they want. How many cars can you put, or passengers can you safely put through that road? But take that exact road, draw lines, put signs, have red lights and green lights, and then have autonomous vehicles driving through them, putting passengers through. All of a sudden, you can put a lot more passengers through the exact same road capacity, right? And it's exactly the same with space. So if you have satellite, as Matt said, if you're responsible with orbits, if you're not leaving trash on the road, or if there's a accident, if you clean after yourself, and you have rules of the roads, and you use technology, all of a sudden you can use more of that capacity. So it is about being responsible and building more advanced technologies that allow us to take advantage of the space that is available to us.
That's great. So you both talked a little bit during your introductions about some of the products that you guys are developing in each of your individual companies. Could you discuss how your products are complementary and how they may be a little bit different?
Take that first.
Yeah, so at LeoLabs, so I can briefly describe what you're looking at here on the screen. This is a visualization showing about 20,000 objects in low Earth orbit right now that we're tracking with our radar network. And what you see in the red there is actually the fields of view of what our radars see when they look up into space, and it auto refreshes every 5 minutes. But so what we really focus on at LeoLabs is tracking those objects, fitting good orbits, and then making data products that can relay risk to satellite operators or stakeholders, okay? So one of our primary services is a collision avoidance service for satellite operators, where again, we track the space debris or other satellites, dead rocket bodies, whatever it is, and we actually compute the risk. It's a probability, it's a percentage between 0 and 1, that those two objects might actually collide with one another. So in reality, they will either hit or they'll miss, and they almost always miss, thankfully, right? You have to be incredibly unlucky for any two objects to actually hit each other in space. Space is big. But when there's tens of thousands of objects and they're going every different direction, you end up having thousands of close encounters every day. And so if you just kind of extrapolate that out over a period of years and years, eventually your luck's going to run out and two things will end up hitting each other, right? So in our collision avoidance service, we do things like compute the probability of collision, and we can also screen if a satellite operator wants to perform a maneuver and get out of the way, we can screen that maneuver for them. So, but actually what we don't do, and we kind of made this decision to focus on our primary mission, we don't compute maneuvers such as we have your satellite model here and the thrusters, and you're going to fire them in this direction and that sort of thing. We don't do that for the customer. We let them do that. But as it happens, that's a big part of Kayhan's job. So over to you.
Yeah. So we, as I mentioned, Kayhan is a software company. We are a data agnostic platform. We get our data from different data sources. One of the main sources of data we have is what's called a high accuracy catalog or HAC that's maintained by US Space Command. We also ingest data from operators themselves. So if you have GPS on board and you have a better measurement of where you are, then we ingest that. And then if you have a customer who, for example, has access to LeoLabs data, we can also get that data as an input. But what we do is, once we decided that our software decided that the risk is too high, and I'll give you some examples. So as Matt mentioned, all of these events are probabilistic. So when you have a conjunction, which is a potential collision, you have a probability of collision for it. Generally, the risk threshold is somewhere between 1 in 100,000 to 1 in 10,000 that operators take an action about that particular event. 1 in 10,000 may sound low, but when you're having thousands of these events, all of a sudden you realize that it adds up, right? And then we don't want to be that unlucky company that happens to it. So when there's a decision that we need to take a maneuver, the model that we have built, so you can imagine that all your satellites have different capabilities. So you may have different thrusters, different forces, different directionality, ground contact time that's required for you to be able to send the command up. And if you want to do this manually, which has been historically done, you take the data, let's say in this case from LeoLabs analysis, and you say, okay, so I have to perform a maneuver. Here's the tracking that I've received from LeoLabs for this particular debris object, and here's where I am. Let me figure out what maneuver I can perform to bring the risk down. So it's kind of a heuristic method, right? But what we have done is we have built all these parameters that you can put in and define your parameters. So this is my thruster capability. These are my directionality. These are my timing constraints, all of that. And you can set a goal. You can say, I want to minimize the risk as much as I can with one maneuver. Or you can say, for example, my goal is to save fuel. So just get me to 1 in 100,000 risk. Bring the risk 1 order of magnitude down. And what Pathfinder will do is that it will, based on your constraints and your capabilities, give you a number of maneuver options that will work for you. They're feasible. And you can just push them to your satellite and you're done. So what we do is the kind of recommending the course of action to get your satellite out of the way. So we don't track, we don't have any hardware. So kind of complementary.
Yeah, another point about that, and tying things back into AWS here, is that speed and low latency are really critical to what we do. So when you're a satellite operator and you, let's say, okay, I have a conjunction coming up and I do want to maneuver out of the way, you want to test that maneuver before you do it, because there is a very slim possibility that you could maneuver out of the way of one object and into the way of something else. Or what if some other satellite operator is going to do a maneuver coincidentally at the same time? Whoops, you both fired your thrusters and you both hit each other. That hasn't happened, but it's feasible. So you want to screen these maneuvers in advance, right? When you do that, you want to screen that test maneuver, which is called an ephemeris. You want to screen that against the other catalog of objects in as current of a state as possible. So you don't want to screen against the catalog of 20,000 objects that, oops, thank you. You don't want to screen against the catalog of thousands of objects that hasn't been updated in 24 hours or 8 hours. You want it to be near real time, right? We pull up our phones and we look at Google Maps and the traffic, and we just automatically, like, it's near real time. It's probably delayed by like a minute or something, right? It's so current. So the way our system works at LeoLabs is that we are continuously updating the orbits of each of those objects in a sequential fashion as we get new data. Object goes over a radar, about 5 minutes later, a new update comes out. So what that means for an operator is, as I screen my maneuver, I'm literally screening it against the current catalog as current as it could possibly be. And let's say I want to rescreen it half an hour later, same exact maneuver. I might actually get different results because some number of objects might have new updated orbital states on them and things have changed a little bit. So because we operate and we scaled our architecture accordingly, there's kind of an older way of doing things. The US government does it this way where you just batch process data. Like you screen every 8 hours on the hour and it doesn't matter what happened in the last 8-hour period. That's worked okay enough up until this point, but it's really not ideal for the scale of like the exponential growth that's happening here. So we really want near real-time data. And because we have architected things the way that we have, we can, from the time an object goes over a LeoLabs radar and we collect measurements on it, to the time those measurements are available in our customer's API, they can pull is about 2 minutes. Doesn't matter what radar it is, where it's at in the world, about 2 minutes later, the customer will have that data. So keeping things as near real time and as near zero latency as possible enables you to know that I have the most current information and I'm making the best choice.
Actually, I'll take it to a different level, right? So both companies, we've decided that we want to build our services on AWS for obvious reasons that it's accessible. But one of the key reasons that we believe that cloud is the only way that this can be done is because our solutions need to be able to provide service on the worst day, not on the best day. On the best day, it's fine, everything works, right? But there are certain theoretical scenarios, Kessler syndrome being the worst one, where you have a chain reaction of collisions, right? So you have one collision, creates debris. Before you know it, that hits another object, and it creates kind of cascading effect. And it can render an entire orbital regime unusable for generations to come. So if that happens, it's an if, right? But it's a possibility. If that happens, all of a sudden, you have all these thousands of satellites that need these services, right? And then that is the moment that your service needs to be available to every single one of those. And that is practically impossible unless you have access to theoretically unlimited resources, which is only available through cloud services. And that's why we've built our systems the way we've built them. We use EKS, we have auto scaling set up, we use serverless databases. We've done everything that we can to make sure that if that happens, on the worst day, our services are still available to who need it the most, because that's when you need to be able to save the assets.
So you talked about, real time, and you talked about, being available for the worst day, and you actually named some of the services that you're already using. I would like to hear more about, what parts of your, critical infrastructure does AWS enable?
I can read off a few services and give a couple of examples of how we're using some specific technologies. But operationally at LeoLabs, just as a high-level overview, we use ECS for compute, S3 for storage, RDS for database, SNS and SQS for queues, Lambda for on-demand computing because the workloads that we have will change over time, and then EMR for ETL and data management. We also actually host our user website on AWS directly and use things like SES for customer emails, notification endpoints, things like that. And then there's machine learning, which is an exciting topic. We are even now doing some machine learning on our scheduling system that our radars use. So you might look at this image and think, oh, the radars are just looking up and they just see stuff, but it's more complex than that. We actually, for most things that are cataloged, we schedule observations in advance. So if you knew where an object was yesterday, you can predict where it's going to be tomorrow, and that'll tell our radars where to look. If you look closely in this image, you'll see in some of the fans there, there's these little beams within the red part, and that's actually what's taking the measurements. So we use phased array radars, and they are steered electronically, not mechanically. It's not like a moving dish or anything. And so you can form these interference beams that will go, and it's kind of like a window, and we'll look and see where these objects are at. Now that scheduling system right now is for 20,000 objects. We're anticipating that to probably increase by an order of magnitude over the next few years, up to 100,000, 200,000, 300,000 objects. So then we talk about scale very quickly. So how do we get from 20,000 to 200,000? Well, we're launching satellites at a faster and faster rate. That's exponentially growing. Occasionally bad things happen in space. Things can blow up. They can make new debris. Occasionally, if you're really unlucky, you can have two things collide. Or these nasty things called ASAT tests, which is where someone intentionally blows up a satellite. Horrible idea, but it happened about a year ago. These things can create hundreds or thousands of new pieces of debris. And we're also trying to track objects smaller than have ever been tracked before. So right now, the sort of historical lowest size that we can routinely track objects is about the size of your fist, maybe 10 centimeters or so. But the number of objects between 10 centimeters and about 1 centimeter is 10 to 20 times that. So the smaller those particles are, the exponentially more of them there are up there. So there's actually many, many more times objects than you see here that are in space right now that represent a threat. But we're trying to track those. That's one of our end goals at LeoLabs. So we're definitely looking at scaling to be able to support a catalog of 250,000 objects or so. And that scheduling system, back to the machine learning point, when we schedule an observation, we want to use every second of our radar time as accurately and as efficiently as possible. So how can we do that? Well, we can look at our historical data sets, the different types of objects. Was it a big object, a small one? What altitude was it at? What angle did we see it at? And we can start to learn when we were successful and when we were not. And we can use that to train our scheduling system to schedule the optimal amount of time for the next observation. So the way it essentially works is if it's a big, easy to track object, like we have no trouble tracking it, you actually need a shorter observation time because you know right where it's at. If it's a piece of debris and it's kind of nebulous, the uncertainties are pretty large, you need a wider observation window to catch it. So instead of treating every object the same, we're using ML right now and training our scheduling system to intelligently optimize those scheduling times that our radar system uses and to compute more accurate probabilities that we'll actually see something on the next pass, which our customers really appreciate.
Perfect. Yeah, I mean, the list of services, I think, pretty identical. So we use S3 for storage, RDS. We use messaging services. EKS is where most of our workload happens, and it's a critical part of what we do. One of the examples that Matt used earlier, and I'll use here. So every time we recommend a maneuver, we have to make sure that's a safe maneuver, right? So every time that you're designing a maneuver, first of all, it's a very heavy process that needs to happen. So with auto scaling, we expand, and then we run these processes, we screen against the existing catalog, and we provide our recommendation. We have some really cool projects that are in the works that use machine learning to detect certain things, kind of, I would say, to find the needle in the haystack. Because as you can imagine, not everything is shared publicly. So there's a lot of contested events that happen. So anyway, so we use another thing that I wanted to mention is the GPU-based computing, and that has been really helpful for us, and especially in the case of Gamut. Anytime that, as I mentioned, anytime you need to launch a vehicle into space, it can be a Falcon 9 or it can be a defensive or an offensive launch. You need to make sure that it's not going to hit anything along the way. So having access to GPU resources when you need them, that's been very that has been at a reasonable cost, right? So that's a big deal. So that has been extremely helpful and useful in developing these technologies for us.
Fantastic. So before we move into Q&A, where we give the audience a chance to ask their thoughts and questions about situational awareness, would either of you like to offer some thoughts about what you'd like to see in terms of the future, whether it's the population of the space belts or whether it's how we track objects better in space?
Yeah, I can take a stab at that. So, I'll start by saying acting responsibly. Imagine, if you're throwing trash out of the window, that wouldn't be nice. That's what the space industry has done so far. So we have all these old rocket bodies that launched payload and they were left in orbit. They're just hanging there and they pose threats. We had a breakup event of one of those a few weeks ago. That one of the really old rocket bodies had a breakup and generated a ton of debris. First, just act responsibly, clean after yourself. So. Recently, U.S. reduced the requirement for deorbiting after end of life for the missions from 25 years to 5 years. What that means is, once your mission ends, you have to demonstrate that you can deorbit your asset within 5 years in Earth orbit before you get a license to launch. And that's extremely important because if you want to launch assets to orbit, fly them for a few years, do your mission, and just leave it there, that is going to add to the debris. So that's just under the same topic. Having maneuverable satellites is key for us to be able to take advantage of low Earth orbit. You'd be surprised, but a lot of satellites that are up there today and they're operational and even are being launched today, some of them are not, a big portion of them are not maneuverable. What that means is they don't have a thruster or propulsion system on them that can change a trajectory meaningfully when it needs to happen. So imagine you have two defunct pieces of objects or two non-maneuverable satellites having a very high probability conjunction or collision event, and there's nothing anybody can do about it. And that's just irresponsible. So having propulsion and acting more responsibly, I'll just stop there. I think those are the two things that I really want to see satellite operators do in the future.
Yeah, I'll extend on that. I agree with everything you said. Accountability is a big thing. The space domain is behind the domains of like land, air, and sea, right? So in the spirit of continuing analogies, if you're driving down the road and you run a red light or a stop sign or something, there's some penalty you have to pay, right? You'll get a ticket, cops will pull you over, something. Same thing if you're navigating a boat or something, or you're flying an aircraft and you veer into restricted airspace. There's penalties for these things from whatever nation or area you're operating from, right? That does not actually exist in space right now. A satellite operator, even if they have a maneuverable satellite, they could receive the highest risk, like, alert, you're gonna hit, miss distance of 1 meter, doesn't even matter. They could get that alert and choose to do nothing. Guess what happens? Nothing. There's no penalty whatsoever. Not only is there no penalty, no one even really knows about it because it was only the satellite operator that got that alert themselves. It's not like everybody else knew about it. So there's all kinds of these scenarios, unfortunately, where operators can kind of cut corners a little bit and do less than the amount that they should to be as safe as possible. So as it turns out, because we work with a lot of the largest satellite operators in the world, the big constellations are really generally the safest ones. They have exquisitely good, they do operational collision avoidance, they have highly maneuverable satellites, they all coordinate with one another, they're doing everything they're supposed to do. What generally happens is a lot of the smaller, like one-off CubeSats or Company X launches their first demo satellite and they just really wanted it to work to get that next investment going. And collision avoidance, let's just not worry about that right now. There's no penalty if they just ignore that, right? So part of it is about really opening up more information and making operators a bit more accountable if they're not following the guidelines. You mentioned another example of the 25-year rule. So again, perfect case. I could fly a lot of companies will fly like their first demonstration satellite just to prove the technology works. Maybe they only operate it for 6 or 12 months at an altitude of, say, 700 kilometers. And then they're like, job done. And then they leave the satellite there and it'll stay there for decades before it actually falls down. So does that really make a lot of sense? Operate a satellite for 6 months and then it's dead and a floating brick at that point, and it stays up there as a threat to other objects now for many, many more years? That's kind of crazy, right? So we're moving in the right direction. All these types of things have been discussed, and unfortunately, we're still in a spot where all we can do is just really encourage operators to do better. There's not a lot of legal ramifications on this kind of stuff yet. It's hard to kind of enforce that. But there are 3 kind of rules that I think, broadly speaking, which I alluded to at the start of the chat, that if we can do those, I think we're in a good spot. One is, if you're launching satellites, make them maneuverable and actually practice operational collision avoidance. The second one is, don't leave your satellites in orbit longer than they need to be, or at least bring them down within a certain period of time. And then the third one is to actually go up and grab and deorbit a lot of the most dangerous pieces of space junk. One of the things we do at LeoLabs is actually not just looking at conjunctions between operational satellites and everything else. We screen everything versus everything. So that means like junk versus junk. Dead rocket body, old satellite, old rocket body, debris fragment, whatever. Anything that might hit anything else, we compute the collision risk for it. Now, as Araz pointed out, even if you see a high-risk event, which we do all the time. There was an event, I think on October 19th of this year, where 2 upper stages of rocket bodies that are thousands of kilograms each, they flew past each other, probably with a missed distance, and I'm not exaggerating, probably about the width of this room, at that speed. Now, if they had hit, boom, just like that, thousands of new pieces of debris at that altitude band, and then they spread out over time, and they're a threat to everything else. So that's actually the biggest risk, it turns out, statistically, as we've modeled it, is not an operational satellite hitting something. It's actually just 2 random pieces of junk hitting each other. And it's going to surprise us one day. It's unfortunate, but technologies such as active debris removal, which some commercial companies like Astroscale and ClearSpace are trying to commercialize now, where you actually launch a robotic satellite, you rendezvous with an object in orbit, and either you have like a grappling fixture or some kind of adhesive, and or a net, and you grab onto it, and then you fire your thrusters, and you actually bring it back down. Really cool stuff. This has been demonstrated a little bit so far. And in geosynchronous Earth orbit, actually, one satellite has docked with another satellite to actually refuel it, which is really cool. So I think there's promising technologies there. It's just a question of can we get them operationalized quickly enough and get everyone to behave as responsibly as they should be until those things happen.
Actually, I want to add something on top of what you said. Transparency is a big thing. You might be operating a satellite today. You may decide to perform a maneuver, and you may not tell anybody. And you may just perform that maneuver. You may check for safety of flight. You may not. And that's not the kind of proper behavior that we want to see. One of the great things that bigger operators do is that they share intent with each other. So if I'm performing a maneuver, whether it's an orbit-keeping maneuver or an avoidance maneuver, I tell folks who are around me that, hey, I am about to perform this particular maneuver. What that helps others do is that if they are planning to do a maneuver, they know ahead of time that you are going to perform a maneuver. One example I'll give you is that a lot of times you look at your constellation and you have no high-risk conjunctions. All of a sudden, you get a notification that within 18 hours you have a high-risk conjunction event. What happens is that somebody else maneuvered in front of you. They didn't tell you, and you only know because at LeoLabs or US Space Command, somebody tracked it, and they identified they performed a maneuver, they calculate the new trajectory for the other satellite, and then they realize that now there's a conjunction. So this can be very risky. So another thing that we encourage everybody to do is that your objects can be tracked pretty well. So it's not like you can hide them. So it is very important, and it's in everybody's best interest if satellite operators share certain types of information with each other. This has been done in geostationary orbit in the past. So it's different dynamics, but without proper sharing and without transparency, it is going to be harder to operate safely in lower Earth orbit. Another thing I want to add is just very high level is that technology that we are developing, both LeoLabs or Kayhan we're developing, can solve a lot of these problems. But technology alone won't be able to solve all these problems. There's a lot of, call it policy making, collaboration, industry collaboration needs to happen to make sure that we will be able to take advantage of this space for a long period of time.
Thank you both so much. We're so happy to have you here with us today.
Thank you.